Hello everyone, this is Raed. Today, I and my group, Rohan, Ahmed, Trish, and Deep, we are going to talk about detecting and alerting a dangerous driving. So, we will start with the outlines. First of all, we'll give you the intuition behind this topic. Why do we choose this topic? And then we are going to talk about two papers. The first paper, a machine learning based defensive alerting system against reckless driving in vehicle networks. And then we will present the limitation of this paper. What are the issues? Because if we were able to know the limitation of the papers, may we can find some solution or some methods to improve these limitations and improve the performance of detecting reckless driving. And then we are going to do the same thing with the second paper, a method of collision detecting using mobile devices. Okay, first of all, when we choose the topic, we get some questions like why do you choose, guys, this topic? Is this topic really important? Is this really crucial to choose or to detect reckless driving? There are like some really bad issues. So and we thought that we are going to give you some facts to see how really important to study some kind of issues like reckless driving. So there is a statistic show that there are more than 90% of the road traffic accidents are caused by human error, which is considered also as a reckless driving. The reckless driving caused 33% of all deaths involving a major car accident, which is mean like more than 13,000 each year. That's really huge. So also there is a 30% of the automobile accidents are accredited to the speed of reckless driving. 30% of all car accident deaths are attributed to driving under the influence, like they taking some drugs or alcoholic. Distracted driving causes about 20% of car accident injuries, and that's also a huge. 69% of people in a survey admitted that they usually talk on phone while they are driving. So all these terms mean that's really bad thing, and that's topic and this issue need to be addressed. Okay, this is the first paper, a machine learning based defensive alerting system against reckless driving in vehicle networks. This paper was published in IEEE in 2019. So, facts about impaired drivers. Okay, reckless driving, also called aggressive driving, which is very conscious act. These accidents are a direct result of negligence. Reckless behavior include, as we told, speeding, failure to yield the right way, or running through stoplights, or like racing, or texting, or driving under the influence of alcohol or drugs. Okay, but why do we need a problem definition? We need the problem definition of reckless driving because the definition of reckless driving in my definition could be different from yours, and the definition of reckless driving could be else in some one aspect. So, is there any standard to what is really the reckless driving? According to the author, they state that according to the Department of Motor Vehicles, a DMV in US, any driving behavior disregarding the safety of other individuals can result in a charge of reckless driving. So anyone that anyone that drive against the safety of other individuals, that can be called as a reckless driving. Okay, example for that: intentionally failing to get the right way, or like someone put someone else in a danger by running a red light or stop signs. Okay, now what are the methods that they are using? Now my friend Ahmed, he will present the method they use in this paper.
Hello guys, I'll take it on from here. So for for their system, they proposed a machine learning based defensive alarming system to detect and alert reckless vehicles. They called it a cooperative driving performance rating, a CDPR mechanism. It utilizes the monitoring capability of vehicles such as inertial sensors, radar, vision sensors, etc., which can be utilized to acquire the information of driving performance of neighbor vehicles and provide a way for neighbor vehicles to monitor themselves, such as the distance gap to neighbor vehicles. They propose the CDPR mechanism to aggregate a vehicle's monitoring data from its current and previous neighbor vehicles. In addition, given the fact that most vehicles can be trusted to drive safely, only the monitored information of vehicles with reckless potential, for example, reckless maneuvering, are uploaded. This is mainly done to reduce the data volume of uploading. So, to support a defensive alerting system, they developed a three-tier system architecture from existing vehicular networks. Supported by vehicular networks, vehicles can communicate with each other as well as with infrastructures, for example, the roadside units. First up is the vehicle monitoring tier, which is this one. It's composed of vehicles moving on the road. Its functions include the driving environmental sensing, reckless driving maneuver detection, and report uploading, and the reckless driving alert reception. Specifically, every moving vehicle uses its equipped sensing devices to acquire the information of surrounding driving environment. Next up is the local aggregation tier. It's composed of roadside units, which are the communication infrastructures in vehicular networks. This tier connects the first and the third tier, respectively, through wireless and wired links. Its functions are to aggregate and forward the uploaded driving behavioral data to locally detect reckless vehicles and to broadcast reckless driving alerts. Third is the global management tier. It's the cloud center. It's the cloud center with strong communication, computation, and storage capabilities. Its functions include globally rating a vehicle's driving performance and sensing the detected alert to corresponding roadside units. The machine learning based driving performance rating models are trained by historical data with reckless or normal labels, which can be periodically updated by the newly arrived data. The label of a reckless vehicle can be derived from the record and from the transportation department, where reckless vehicles are the ones intercepted and charged by the traffic police. Next up, this is the algorithm that is at the participating vehicles. You can look through it when you want. This is the algorithm that's at the cloud server. Um, you can check both of the algorithms either in this file or in the papers when you want. And next up, I will leave you with Rohan. He will take it on from here. Thank you, guys.
So, as per the paper, the non-intrusive detection of drunk drivers, they have discussed the types of accident based on three causes. The vehicular cause, which can be caused due to tire punctures, brake failures, and so on. The behavioral cause can happen because of the driver is intoxicated or drowsy, or maybe a rash driver. Such things can happen only during a particular period of day, like drowsiness can happen mostly during night time or driving alone, or can happen only on particular roads like highway. Environmental cause can be due to extreme weather conditions. Also, the type of vehicle plays a big role here. A small car is not as dangerous as compared to a big truck while driving on a foggy road or a wet road. We can divide the detecting into two categories, vehicle based and person based. We can monitor the vehicle for different types of signal like lane correction, sudden increase and decrease in speed, and so on. The person based the person based detection can be monitored for the signals of drowsiness or intoxication shown by the blinking of the eye, frequent yawning, and also the heart rate and so on. Let's focus on the person-based detection, and the normal flow of the algorithm is as shown on the screen. As the loop shows, the detection will run iteratively after some time till the car is running. It will monitor the driver over the entire drive, and if found impaired, it will alert the driver himself and the cars in the surrounding. To detect drowsiness and drunkenness, they have used two methods, using camera and using ECG. Using camera, we can detect the face, eye, retina, and then figure out or predict the blinking of eye, the no, frequency of yawning and nodding of head, which helps to detect drowsiness and drunkenness. The problem with detecting drowsiness or drunkenness is that the camera can only work in proper lighting conditions. If there is too much lighting or not or no lighting at all, it can have a major effect on the accuracy of the algorithm. But as you can see, using the camera with IR illuminator using the Berkeley's derivation method, we can attain a 99% of accuracy. Also, there are other classification algorithms and other cameras used, as you can see in the table. So we have LDA algorithms, SVMs, neural classifiers, which give approximately 90 to 92% of accuracy using the facial signs to detect a impaired driver. Now, there's also another kind of detection which uses the heart rate. Now we can use this ECG, and it is very much reliable compared to the face detection technique. Different algorithms like LDA, KNN, SVM, neural networks, and hidden Markov model are very good in accuracy compared to the ones discussed before. But the problem with this is its cost, which will make the sensors to be installed in every car, and there will have to be an incentive to make people use it. So it is not a good technique to use such a sensor-based techniques. Now, as we have discussed the pros and cons of both the methods, we have decided to go with face detection as the paper suggests. Now, let's consider the face detection based on a video. So they have extracted the videos from the NTHU database. Now they extract the images 30 frames per second to be precise from every video frame. Then out of those images, to represent every image, they have taken something called as landmark coordinates of this image using a dlib library. This library gives a 68 2D coordinates, or else called as XY coordinates, to describe the image. After this extracting of images, we can train this algorithm and deploy it. Now further, Teerth will go in depth about this multi-layer perceptron algorithm.
So I'm going to take the non-intrusive system for detecting drunk drivers in modern vehicles. So this paper used inertial sensors, the car telemetry, and the road lane data to detect whether a driver is impaired or not. So, of course, before going there are multiple ways to solve the same problem. So these people have found out a lot of research related work corresponding to the same problem. One way to solve this problem was using parallel sensors on the road borders. And if a particular car goes over these sensors, then we detect that this is a drunk driver. The transdermal sensor, on the other hand, gives you the blood alcohol concentration levels, and if it crosses some threshold, we say that the driver is impaired. Human breath also gives you important information about the alcohol levels in a human. The driver pulse and inertial sensors also give important information. Looking at what this particular paper did was they created a naturalistic driver behavior dataset in order to detect whether a driver is impaired or not. So they created this in a simulated environment. They took two sets of people. One set were the normal drivers, and they were told to drive for 10 to 15 minutes. And in this 15-minute interval, they took the inertial sensor data, the car telemetry data, and the road lane data. After that, the same set of people were given goggles that simulated how a drunk person could view the roads. And after that, using these goggles, they were told to drive for another 15 minutes, and this data was sampled on the other set. One data was labeled as no risk data, and the other was labeled as risk data. The features that they used were the acceleration, the speed pedal level, the brake pedal level, the steering wheel angle coming from the car telemetry. On the inertial sensor side, they used the accelerometer and the gyroscope readings for the X, Y, and the Z axis. The lane and the road, they also used the lane and the road information, as in how far is the vehicle from the center of the lane, what is the angle of the vehicle with respect to the lane, were also important parameters to detect whether the car is moving in the correct direction or not. So how was the system designed? So they first acquired this data from the database and extracted the important features. And they checked if there is an end of the period. The end of the period comes when there are 220 frames. If there is an end of the period, you calculate the mean and the standard deviation for each of the features. Once you calculate the mean and the standard deviation, you pass it into the MLP-based neural classifier that classifies the data into risk and the non-risk. The rating buffer contains the entire entire predicted labels over the end of the period. So 220 frames precisely. If 65% or greater is labeled as a risk, then the overall system says it's a risk at this moment. Next, what are the key takeaways from this particular paper in our project? If we look at it, these people have used the pattern recognition technique to detect if a person is drunk, or if a person is dangerous for driving while driving. So yes, we can use the NDBD data set. The accuracy for this model that they got was 98%. Of course, they got it in a simulated environment, but still 98% is a very good accuracy. However, the challenge comes while picking up the lane data and the data from the car telemetry. That is a challenge, and it's an open question at this point of time. The simulated environment, what kind of simulated environment have they used? They have not really specified exactly. And how do we create a simulated environment? Moreover, there is also further work, as in we can use gestures of the driver to detect whether a driver is drunk or not. We can also extend this project in this fashion. Next is the driver drowsiness detection for Android application using deep neural network techniques. Rohan has covered the first part of this, and I will be just taking what an MLP network is and how do we train this particular network. So if we look at this multi-layered perceptron, there are three layers: the input layer, the hidden layer, and the output layer. The input layer takes the input from the images. The XY coordinates, the 68 XY coordinates mapping each point to a facial feature is the input, as Rohan suggested. Initially, we take random weights to each of the links, and we calculate the input times the weight and sum all of these weight and give to a single perceptron. The next goes into the output. In the output phase, we calculate whether the value goes above threshold or not. If it goes above the threshold, we say that it's a risky label basically. When you go back after calculating the error, and we keep on changing the weight functions after calculating the error at the output. This is how backpropagation works in the multi-layered perceptron. The model preparation was spoken by Rohan. I will be talking about how they proposed the architecture for the Android. So they had a Java native interface where they extracted the images from the camera. After extracting these images, they used the dlib library to convert this image into 68 XY coordinates, and then they passed it onto the driver or drowsiness detection application, or in other words, our MLP. And this MLP gave us whether the driver is drunk or not. So what can be used in this? Of course, we can use the dlib library to extract the facial features that they used. They have not used the vehicle-to-vehicle communication here. And we can do the vehicle-to-vehicle communication, and we can add this to a feature in the app. So, and the data set also, we can use the data set NTHU in our project. The next vehicle-to-vehicle communication would be taken by Deep Gosalia. Thank you.
Hello everyone. In this presentation, I'll be showing about the V2V network and also about the motion sensors present in the smartphone. So first we'll be seeing the V2V network and the internal parameters and the trade-offs affecting it. So basically, as we know, the V2V communication basically the sending messages of the data via the between two or more cars. And the underlying architecture could be using the Bluetooth, using Wi-Fi, or using Zigbee. The other alternative to the V2V is the V2R, which is nothing but the vehicle to roadside unit. So in the roadside unit, as you can see, it covers a wider scope. But the main advantage of why we are using V2V instead of V2R is that V2V is much faster, because in V2V we first send in V2R we first send the message from vehicle to roadside and roadside to vehicle. So that causes some delay. And that's why we prefer the V2V communication. And there are also some application about the highway safety restrict level, which we'll be seeing later. So what happens behind the scenes of V2V, or what are some parameters of how the message is sent and what technology to use? We'll be comparing each of them. Now, the main two parameters are the association time and the data exchange time. In the association time is basically the time to establish the connection between two times, and then we send the data, which is nothing but via the data exchange time, which depends on the speed of and what kind of infrastructure we are using. So there could be two scenarios. One is the cars traveling the same lane or in the opposite lane, depending on that we calculate the relative speed and compare it. And also there is another thing called transmission range, such that each car has its own transmission. And if the car is within that transmission, in that range, then it can receive the message successfully. So if we compare then, as we told earlier, that we have two times. One is association, which is A, and the X, which is an exchange time. And this total time is less than equal to the L, which is nothing but the available time. If we see this formula, then L is equal to dVIG upon VL, which is nothing but a speed equal to distance upon time. So what we see is that if the distance, if we see the relative velocity, if the relative velocity is tending to infinity, then the L decreases. L also tends to 0, so we have very less time to establish connection and association. And the same way, if it tends to 0, then the L, we have much time to establish connection. As you can see in the graph, if you just see the curves, then as the relative speed increases, then the time we have to establish everything and sending the data also decreases. So now comes the data exchange, and it depends on what kind of infrastructure we are using. It could be Zigbee, Wi-Fi, Bluetooth. In the research, it was suggested that if we are using Bluetooth, then it does not work very well after 10 miles per hour. Same for the Wi-Fi, which does not gives the result after 90 miles per hour. But for the Zigbee, the results were really good. And then comes the probability of success, like what is the probability of a connection to be successful and the driver successfully receiving the data. So if the association time, that is the time to establish connection, increases, then we have very less time to have the to send the data. So in that case, the probability also decreases exponentially as the association time increases. Now coming to this second paper here, we'll be seeing about how the motion sensors can be used from the smartphone can be used. So first thing, what we mean by invisible sensors are nothing but the accelerometer, gyroscope, and magnetometer. But why do we want to use this instead of cameras? So one of the things that paper highlighted was that if the conditions like the surrounding environment conditions like lighting, weather, or some kind of or the weather is very harsh, then the cameras won't provide the accurate result. In that case, we use the invisible sensor, which will definitely provide the result. But another thing is that using cameras, it provides it has very what do you say is a computational. It takes much computational resources. So if the user is using like a old device, then it has very less RAM, like say 2 GB, 3 GB. Then it will require computation, and the result, like the data, won't be received at time. So with those things in mind, we go with the we use the mathematical model of the underlying architecture, that is inertial measurement unit of the using these invisible sensors. So after going through that, we have the other applications. We'll be seeing later about the like driver careless detection and lane change, everything. So coming to the procedure, which is the main part here. Now in this, you can see that is the first thing that we need to do is the align the smartphone with the car, and such that it must remain static, and so it will provide a better result. So in this case, you can see the below 4 graph, in which if we make a left turn, then the curve, there is one positive bump. In the right turn, there is a negative bump. And for the left and right, there are 2 bumps, positive and negative respectively. So this readings are generated from the gyroscope, and it can also be, you can verify it using some smartphone app. So coming to this, let's say this bump of the right turn. In this, so how do we determine, like in the implementation part? So what we do is basically we check the cutoff, like if it goes beyond delta H, then we know that a bump has arisen, and if it crosses delta H, then we wait for the bump to end. In that way, we can easily determine like how many bumps are there. If it is 2, then we can see it is either left or right. So that was about the single line, but what about the curvy roads? So if we use the previous algorithm, then if the driver uses the make a curve, then it will say that it is a left turn, but actually it is not. So in using that, we also consider the second parameter, which is nothing but the horizontal displacement. So considering the US, generally it is the lanes are generally 2.7 meter wide. So if the driver is moving and if the displacement is less than 3.7 meter wide, then we can say it is a curvy road. But if it goes beyond 3.7 meter, then we can say that there is some displacement and there is some lane change. So that's how we measure for the curvy road. Here you can see out how we can generally see in the straight road, or using the basic geometric trigonometry, you can find what is the length of the change in the path. If it is greater than 3.7, we say that there is a lane change. Now coming to the alternative IMU. So here we're considering the inertial measurement units, that is the accelerometer, gyroscope. But what are the other things? Like we have GPS, we have the other thing. If you take the GPS, then it can provide the velocity, whereas the IMU provides the acceleration. Now GPA output rate is much less. As you can see in the graph, the output rate is much less. So what we can do is we can combine the acceleration and the velocity using the Kalman filter. The Kalman filter is nothing but which takes the multiple measurement and makes one curve. And it provides a very good result compared to others. And the paper also suggested using other formulas to remove the noise from it. Then comes a further work and application. So how we can use this? So there is another thing like detection of turn signal. So what the paper does is that if the driver has not started the turn signal sound, then like if it is turning but he has not indicated to the other user, then it is definitely like we can check using the some sound meter. And if it is not, then the driver is driving carelessly, and we need to send it to the other drivers. The other application could be a fine grid lane guidance. So as you can see, if the driver makes a very big curve, very big turn, like crossing the radius, like it was observed that a normal radius R1 and R2 will be like 13.1 meter, and for this side going from this lane to the left side is 21.64 meter. So there is this is some threshold set by the paper after connecting many experiments. So if the curve or the radius goes beyond this point, then we can say we need to send the signal to the other driver and warn them. So that was whole about this presentation we have discussed, and from all the reference paper we have referred. And so thank you. And if you have any doubts or want to discuss something, you can definitely comment in the discussion, and we'll definitely also discuss in the class. Thank you.